Imagine you're trying to build a complex new medicine, but your building blocks, the atoms, are completely invisible to the naked eye. That is the daily reality for pharmaceutical scientists. To see these invisible structures, scientists use a machine like this, an NMR spectrometer. It uses giant magnets to listen to the faint magnetic pulses given off by individual atoms. Usually, this machine prints out a one-dimensional graph, where every atom gets its own spike on a line. But when you are dealing with a large drug molecule, you have hundreds of atoms all shouting at once. Think of it like looking at a dense city skyline from miles away on the ground. The buildings overlap so much that they merge into a single jagged wall of shadows. Because these atomic signals pile up on each other, you can't see the streets between them. You can't tell which structure connects to which. That standard graph gives you a list of ingredients, but it leaves you without the information needed to assemble them into a safe, working medicine. To make sense of that crowded city, you need a new perspective. You need to fly a drone straight up and look down at the street grid. That is exactly what two-dimensional NMR does. Instead of cramming every signal onto one horizontal line, 2D NMR spreads the data out over a large flat grid. It pulls apart the overlapping voices so each one has room to be heard. The main atoms line up in a neat diagonal row. But the real secret is hidden in the empty space. When mysterious cross peaks appear off to the side, their path back to the main line acts like a bridge connecting two specific atoms. Even if two atoms look identical from the side view, their unique intersections on this grid show exactly which molecular street they live on. By shifting into two dimensions, chaos becomes a structured grid, finally exposing the hidden connections that were previously buried in the noise. Scientists don't just use one map. By tuning the radio pulses of the machine, they can draw different kinds of relationship networks to uncover exactly how a molecule is built. The first map is called COSY. Think of it as a map of who is holding hands. It specifically highlights atoms that are physically bonded together, tracing the rigid skeleton of the drug. Then there is NOESY. In this image, notice how hydrogen atoms, HA and HP, are not linked by bonds, but sit next to each other in physical space. NOESY detects atoms that become close neighbors when the molecule folds up. Knowing those neighbors is critical. A medicine's ability to help you depends on its physical shape, which determines how it docks into the proteins in our bodies. Finally, there is HSQC. This acts like a family tree, linking different elements together. It specifically pairs every single hydrogen atom to the exact carbon atom it is attached to. By layering these maps, researchers can confirm exactly where every atom sits and how they are all linked, providing a verified architectural blueprint. In the past, gathering all these detailed maps was a slow process. A single scan could tie up a lab for days. Today, scientists use ultra-fast 2D NMR. Through specialized radio pulses, they can capture the entire two-dimensional grid in a single scan that takes less than a fraction of a second. Because it works so quickly, researchers can watch fast chemical reactions unfold in real time. They can observe unstable medicines as they form, watching chemistry happen live. To handle this rapid flood of information, laboratories now use artificial intelligence. These algorithms instantly sort through the dense grids of crosspeaks, spotting patterns that would take an expert much longer to solve. Scientists can now combine all these connectivity maps to generate a detailed 3D digital model of a potential new medicine, where every bond has been confirmed by experimental data. Two-dimensional NMR takes the messy, overlapping noise of the atomic world and turns it into a clear, navigable grid. It gives us the precise tools we need to design the medicines of the future, one molecular street at a time.